require energy, and you can't break them apart because, yeah, you can't fuse them, would require energy. Splitting them apart would take energy, right? So stars end with that. That's like the ashes, right? So this is what we got so far, right? Hydrogen fusion stops, the helium core collapses, it puffs up into a red giant, right? And then it goes, uh-oh, collapses, does helium fusion, right? And then the carbon core collapses. If you've got enough mass, you actually can become a white dwarf. Now, sadly, our sun isn't even going to make it there. It's like, that's sad, right? We don't think we have enough mass. But eventually you become really small, right? These things are about the size of planets. White dwarfs are about the size of planets. So you get really, really small. By the way, what happens to your spin rate? Yeah, if the sun spins, every 12 days or something like that, or whatever it is, right? I can't remember what the period of this. Does anybody know? Anybody take astronomy? It's like days, I think, for it to go around or something, right? How fast is it going to spin if you crush it down to something the size of the Earth? That's a lot of crush, isn't it? Yeah, it's going to be spinning really fast. So these guys spin. That's what makes those really pretty pictures, those planetary nebulas, is that spin. Okay. So anyway, this thing collapses. Eventually you get a white dwarf, right? Okay. And if you have to have 0.7, greater than 0.7 the mass of the sun. Remember, our sun is going to be at this point very small because it's going to be, when it explodes and does this thing, it loses a lot of its mass right there, like 3/4, 7/8 of its mass. They're not sure. Okay. Now, here's how we know this. Globular clusters are groups of stars that were born all at once, right? And if you make an HR diagram of these things, right? This is an HR diagram of a globular cluster. Now, what happened to all these stars out here? Where'd they go? Connor. Alan! What happened to all these stars here? Where'd they go? They're not there. Why aren't they there? Why are these stars gone and these guys aren't gone? Which stars live the longest? These guys live the longest. Which ones die the soonest? These guys, yeah, blue ones, the big giant blue ones on the left side here, right? These guys live the shortest amount. So where have they gone in this globular cluster? They've died. Where are they going? They're heading off. They're becoming red giants, right? So this is like a road race. If you could see an animation, you'd start off with the whole main sequence, and then one by one they'd peel off and they'd do something where they'd go out here and they'd expand and all this stuff, right? Along about here or about where our sun is, these guys are turning into red giants. Okay, that whole thing where they do the little expansion and then into the white dwarf happens so fast that you don't see it on there, right? Okay, but anyway, this is how we know it is. It's like we analyze those things, right? And it's like, okay, there we go, right? Okay, now, if you look at these pictures here, okay, planetary nebulas, what they've got is you've got a couple white dwarf stars. Probably you have a system of 2 stars. Most stars, like 80% of stars, have a stellar companion. There's another star next to them that they're orbiting. So it's like the star, the Tatooine orbits is a binary star, yes, in Star Wars, right? These guys orbit each other, kind of like this, okay? If one of them is a white dwarf, okay, what can happen is that this guy, as he gets close to this guy, can shoot stuff onto him because these white dwarfs have sort of a blousy sort of atmosphere around them, okay? And so if they orbit, especially if they've got it's like some orbital trajectory that carries them like close to each other, like this far away and close. I think I showed you. Did I show you those orbits? I think I forgot to show you. Now interactive physics doesn't work. It's sad, right? Okay, but they can have an orbit where they get close to each other and then far away, and close to each other and far away. In fact, most of them are fairly elliptical, right? If they have that orbit, every time they get close, the white dwarf can get perturbed. When he gets perturbed, you never want to perturb a white dwarf, right? When he gets perturbed, he shoots stuff off in random directions. And remember, these guys are shooting material this way and this way at the same time. These are those polar jets. The same type of jets that protostars have, right? Black holes have them, neutron stars have them. Rapidly spinning things have these jets, right? So in this picture here, what's happening is that you've got a situation like this, and the distribution in space is actually like this. A lot of them look like hourglasses, like that. Now, we're not looking at it from the side. We're actually looking at this thing this way. Yeah? We're looking into it, so we're looking into one of those circles, into one of those, right? Does that make sense? Right? In the center, there's that white dwarf. That's the thing that's been, and basically this guy's doing a stately dance. It's shooting stuff off of its little poles, and it's sort of gyrating around like a top. A lot of them make this. I'll show you other pictures of this. So it's spinning, it's precessing like a top. It's going like this. Yeah, you ever play with a top and like before it falls, it kind of does that, right? Okay, this is called precession. So that's what they think is going on here. This one is chaotic and random. Okay, it's shooting stuff off in just random directions. Again, this is just point symmetry. It's not even bilateral symmetry. Okay, this is pretty good. This is like hourglass shape, right? And we're seeing it right from the side. Again, it's just spinning like a top, right? There's another companion that's making it precess. Taylor, your ship has arrived. They want to interview you. This is the Cat's Eye Nebula. Again, this one is more chaotic. It's sort of like if you threw a wet rug in a spinning a washing machine, what would it do? Yeah, it's going to hop around your basement and just do a little dance, isn't it? Yeah. So that's what's going on here, is that this guy's shooting stuff off in the other directions, and it's whatever its companion is doing unpredictable and sort of random things to it. It's like colliding with it and throwing stuff onto it. And every time it shoots stuff off, it always shoots stuff in both directions. So here's one side, there's the other side. Here's one side, there's the other side. One side, the other side. It's point symmetry. This and this. It's not perfect, but it's there, right? Okay. Again, this guy is like, that little moment of whatever it is, right? Boom, boom. This point and that point. It's three-dimensional, so you can't always see it when it's flattened in a picture like that, right? Okay. Now, if you stop at this point, if you're a white dwarf and you cool down, now the question is, what's going to happen? If you cool down, what's going to happen? Is gravity going to crush you any farther? Well, there's something, okay, if you get to about 1.4 times the current mass of the sun, right, our mass, right, if it's less than that, nothing happens. It just cools down and becomes a star cinder. It's degenerate matter, right? So it's no longer like atoms the size of the Rose Garden arena. The nucleus is like pick some small object, a golf ball in the middle, and the electrons are buzzing at the edge. Have we heard this analogy for an atom? Right? It's no longer that. It's electrons and protons, cheek and jowl, occupying some space, but not. It's way, way more dense. Okay? So a white dwarf it'll become a white dwarf about the size of a planet, about the size of Earth. Right? So if it's less than 1.4 times, right? So if the mass is less than 1.4 times the mass of the sun, right? Then it just becomes a star cinder. It just cools down and there it is, right? Okay. They call these black dwarves. Look at this. Now this, I actually won a PowerPoint animation award for this. Watch. Huh? Kind of makes you feel it, doesn't it? Yeah. Yeah. Right? So now it's like, now the fun stuff starts, right? Okay? Like, ooh. Okay? If it's greater than 1.4 times the mass of the sun, something really special happens, right? Okay? Now its mass is greater than 1.4 times the mass of the sun, right? This is something called the Chandrasekhar limit. So let's all say that word. Chandrasekhar. There we go. It's Subramanyar Chandra. I've looked it up on Wikipedia and I don't remember. But he's a guy, he's from India. He was from British India, which is now Pakistan. Okay? If it's bigger than that, okay, the thing that props up this is something called the Pauli exclusion principle, which says, did you guys do orbitals in chemistry class, like how to fill the orbitals with electrons? Did you do that? Okay, do you remember there was spin up, spin down, you filled them like that, remember that? Right? Or there was something like that, right? But only so many fit in an orbital, correct? Yeah. The thing that makes it so that they can't fit any more in there is that there's something called the Pauli exclusion principle. It says that two electrons cannot occupy the same quantum state. Well, that's what this is about. If it's less than that, then the Pauli exclusion principle props these things up and they just sit there and go, I don't like being this close, but that's as close as I'm going to get, right? If it's bigger than that, gravity violates the Pauli exclusion principle, crushes the star, and it crushes down from something the size of the Earth to something the size of Portland. Now, there's two reasons why this is a bigger deal Okay, the first deal is that that's a much greater